Good afternoon, everyone. I'm Milad Moosavifar from University of Michigan, presenting our project, which is an aluminum nitride and silicon resonant IR sensor array with an enhanced TCF. So the research in our group for the past few years has been to develop passive IR sensors in order to detect IR in different wavelengths, starting from the near IR, going all the way up to long wave IR. Uh, Most of us have heard in the news or read on the internet about the usages of IR imagers. Uh, for instance, I personally read last week on the website that police has been granted for new funding to buy new equipments for night vision with IR detectors, so that they can find people who get lost easily, especially the elderly people who sometimes wander around and forget the path. These devices range a few yards, few hundreds of yards. Or back to 2013, there was a bombing attack in Boston's marathon, which again, this was the IR images which helped the police to handle the situation. So IR sensors basically provide us the ability to see actually in unclear environments with dust or with rain, or environments with lack of illumination like night vision. So IR imaging is usually achieved by generating a thermal map of the surrounding environment. As every system is shrinking with the pass of time with the newer technologies, IR detectors also are required to be shrunk. So we've been trying to reduce the size as well as enhancing the performance of the IR sensors. So IR detectors basically fall into two parts, two categories. The first category are the cooled detectors, which provide us with a better image quality. They have lower noise, and actually they consume higher power, and they're larger in size. But the uncooled detectors, which are smaller, and the quality of their image degrades slightly, fall into two parts. The first one are the non-resonant detectors, which an example for these detectors is the bolometers. And then the other one are the resonant detectors, which we've been working on for the past years. The materials used in these sensors are gallium nitride, aluminum nitride, silicon, or silicon dioxide, etc. As an example for non-resonant IR detectors, all of us might be familiar with microbolometers, which are which basically absorb IR, and their temperature changes based on the amount of absorbed IR, and their electrical resistance changes, and this change in the electrical resistance can be read out, and the thermal map or the thermal image can be generated. These devices, however, have been there for a long time, and they've been well developed. Their fabrication is relatively cheap, but they have some downsides. One of them is that they're relatively large in compared to our devices, and then sometimes they dissipate a lot of power, and sometimes they require cooling as well. So in our approach, which we've used the resonator-based sensors, the way that it works is that we basically use the resonators as sensor pixels. So each pixel is covered with an IR absorber layer, and then the temperature of each pixel changes based on the amount of absorbed IR, which depends on the efficiency of the absorber layer, the thermal properties of the resonator, the frequency of the IR, and the efficiency of the absorber layer. So when the IR is absorbed, the temperature of the resonator changes, and this temperature change leads into a shift into the resonance frequency. And this shift can be detected, and the amount of absorbed IR can be read out. To show the proof of concept, we started with gallium nitride-based devices 4 years ago. We use the piezoelectric property of gallium nitride devices so that with a change in the temperature, a charge and then a resulting net voltage was induced in the body of the in the resonator body, and then this caused voltage caused an extra stress in the resonator, and that led into a shift into in the resonance frequency, and this frequency change can be read out. And we also tried different absorber layers for these devices, including silicon nitride, carbon nanotubes, to check the selectivity of the IR for different wavelengths. Then we moved on to aluminum nitride-based resonators because they're CMOS friendly and they can be built on silicon wafer, so they can be integrated with commercial CMOS process. And then we designed flexural mode devices, and we could measure a TCF of minus 27 ppm per Kelvin, and TCF stands for temperature coefficient of frequency. Here we have a comparison table for the resonators based on different materials. Silicon oxide and silicon-based resonators are kind of the old ones. Quartz has the downside of not being integrable. Aluminum nitride and gallium nitride demonstrated the best performance. However, aluminum nitride was the only one that was integrable with CMOS process. Gallium nitride is integrable with gallium nitride HEMT circuits, but it's relatively expensive. So for commercial usage, it's better to move on to aluminum nitride. Here comes up a question. Is there any way to enhance the TCF without changing the material used in the resonator? To answer that question, let's take a closer look to the mechanism of the frequency change due to temperature change. So if you have the resonator here, and if you take a closer look at its anchor and the resonator beam, we have a silicon layer on the bottom, then an aluminum nitride on the top, and an extra layer of silicon oxide on top of the resonator beam. So in the room temperature, the beam is under tensile stress because of the mismatch between the thermal expansion coefficient between the silicon dioxide and aluminum nitride and silicon. As the temperature goes up, this stress reduces, and then this causes the resonance frequency to go down. And also, as the temperature goes up, generally the stiffness of the material, the effective stiffness of the resonator reduces, and this causes the resonator resonance frequency to reduce. Factors from 2 and 3 go hand in hand to decrease the resonance frequency of the resonator as the temperature goes up. So the effect of this of the temperature changes into the resonance frequency can be compensated, and is usually compensated in the resonators, especially when they're intended to be used in the clock or timing references. For instance, in the previous work in Berkeley at 2000, in a flexural mode device, passive compensation was used to compensate the frequency change, as you can see here, along a wide range of temperatures to generate a robust and kind of fixed resonance frequency along the temperature range. But because we are seeking to develop a sensor, we are trying to amplify the resonance frequency change due to the temperature change. So we are moving in the opposite direction. So we are exploiting that causes stress to achieve a larger frequency shift. So we want the causes stress due to temperature change in the resonator to be larger so that the resonance frequency change is larger. So in our sensor, for this purpose, we have silicon in the anchors. We have silicon on the bottom. Then we have molybdenum, and then aluminum nitride and aluminum on top. On the resonator beam is the same thing, except that an extra layer of 2.5 micron of silicon dioxide is deposited on the top. And the mismatch in the temperature coefficient of uh, expansion of the silicon dioxide and the other layers causes that extra stress. So the reason that we are looking for a high TCF is that basically it results into a lower noise equivalent temperature difference, or let's say lower noise in IR detection. And then here we have the stack cross section of our commercial CMOS MEMS process, which we collaborated with InvenSense company to fabricate our devices. On the bottom here, we have the only MEMS wafer. So I should mention that the thickness of the different layers and also the type of materials that we are allowed to use in our resonator design is limited by this commercial fabrication process. So we cannot select arbitrary values for those thicknesses and also the material types. And then on the top, we have the CMOS wafer here bonded to the MEMS wafer. And the CMOS process used on that is a 180 nanometer. And the benefit of using this process is that the CMOS and MEMS can be bonded together into a single chip, enabling to design an autonomous and integrated IR detection system. Here we have the measurements of the devices fabricated. The device shows a resonance frequency at 4.6 megahertz with a Q of 1100. And then the TCF measurements demonstrated a TCF of minus 136 ppm per Kelvin, which is really promising in compared to the previous work on the same process. We could improve the TCF more than 4x. The previous TCF measured an aluminum nitride process was minus 30 ppm, about minus 30 ppm. And this designed IR sensor is going to be used in an IR imaging system. So the way that we can read this sensor out is to generate a periodic signal with a frequency close to the resonance frequency of each resonator, and then select each sensor at a time. So if we have an array of sensors, we select one at a time, and then excite each sensor, each resonator, and then the excitation is cut off, and then ring down signal with the exact same frequency as the resonance frequency is generated. And if we boost that signal up and amplify that, we can generate a square wave signal, which has the frequency the same as the resonance frequency of each resonator. And these resonance frequencies can be compared to a reference resonance frequency, and the amount of the absorbed IR can be extracted for each sensor pixel. Then here in the end, we have a comparison table for the previous version of the aluminum nitride in our group, the gallium nitride version of the IR detector, and the current aluminum nitride design here. So we have shrunk our device considerably, and it's real beneficial because it provides us with a higher density of sensor pixels, and it improves the quality of the generated IR image. And then the readout circuit for this type of sensor is real low power because we've chosen the ring down method, which consumes a much lower power, and because the resonance frequency is also low, so it does not require much of power. And then the TCF, as I previously mentioned, has been extremely improved more than four times. And the main benefit is that aluminum nitride process is, again, CMOS compatible and can be integrated with CMOS circuit. I'd like to thank ARL for funding us and helping us during this project. And also, I'd like to thank InvenSense company for collaborating with us and fabricating our resonators and CMOS. Thanks.